Okay, so we are discussing about the lecture 3, 2037. Can you see central processing unit?
Yes, sir.
Yes, sir.
How many slides we have covered?
65, sir.
65.
65. Okay, so yes, we are discussing about the pipelines. Let's start it from the 64. Yeah, we are discussing about actually that what is pipeline. We have already said that, I mean, in the fetching that we said as because our main memory is slower than the processor. That is actually a huge problem when the CPU is doing something and uh, and it needs something to continue its operation. So it's have to go to that main memory. Okay, so this is actually a problem because the main memory is the slower memory compared with that your CPU. But I mean the CPU is going to be stalled. That means CPU is going to be stopped when he requires something. So if it is not there, then that the things must need to be bring from the memory. So in that case, the when he is CPU is requesting for that the instruction from the memory, so the CPU is going to be stopped. CPU is going to be stop working. CPU is going to be pause. So until I mean when that the from memory that the CPU is going to be retrieved that the instruction he was looking for, then only it is going to be play. The I mean continue um, its operation. So that is what the main problem. I mean we are discussing for the long time, and we have seen that. I mean this problem has been significantly reduced or significantly improved by the cache memory. That one technique we have already discussed several times, that the cache memory can actually reduce that the problem because the cache memory is going to be the nearby memory inside the CPU. So that is what I mean. You do not need to go to that the slower type RAM to get back that the instruction. So CPU does as when the cache memory is going to be there, CPU does not need to actually wait for a long time. It is going to be get that the instructions from the cache memory that you have learned. So another technique you can see here, that is the pipelines technology. So the pipeline architecture that we're talking about, so that is the part of the fetching, right? So this is what actually we're discussing, that cache memory you have learned. Now we are talking about the pipeline technology. So how that the pipeline technology will overcome this situation, that I mean that the CPU needs instructions while he is doing some operations. So how actually the pipeline technology is going to be help to the CPU uh, to work with the instructions faster. So that the second technology that I mean we are second technique that we are actually explaining here, the pipeline. So we have said that the pipeline technology that going to be improved instruction execution speed by putting the steps into parallel. So that is that is the common technique also into that the computer system, as we have discussed it many times, that yes, when we have talked about the parallel processor, we have seen that I mean it has been the same concept was there, that okay, I have that the multi-core processor, so that means when I have the multi-core processor, so the work are going to be given parallelly. So at the same time the two works can be executed. Four core processors, then the four works at the same time can be work the simultaneously. So that is what I mean. We have seen also that in case of the instructions, that when we discuss about the sys chips, RISC chips. So in case of RISC chips, we have seen that I mean we are actually dividing some subgroups that we call that micro ops. So the that is going to be divided into micro ops, and that is going to be easier for the computer to execute the things sequentially, execute the things at the same time. So here, this is what I mean. We said about that the system clock. There we have said that I mean we have seen that for executing an instruction, it must need to go for that four clock tick, that fetch, decode, execute, and store. So we have said later on that no, we are having now the multiscalar processor. Now that the processors are with the gigahertz of speed, so that means they will be able to do multiple executions in a single clock. So that means I mean our processing time, our execution time is going to be reduced significantly. So this is what the same technique we are bringing here, that actually it is telling the pipelining is going to be improve the instruction execution speed by putting the step into parallel. So that is what actually that again, I mean we are seeing that the similar type of techniques are there in case of the pipelines. So it said instructions are sent from the software and broken down into micro ops, that the smaller sub operations in the CPU. So that is what I mean the discussions we have been, that when instructions are coming to that the CPU, it capable to actually break down those instructions into subgroups, into that the micro operations, and this decomposition and execution takes place in the pipeline. So that the pipeline is a technology that where you will be able to use or able to give that the different the same instruction, you are making the sub operations, and then you are going to be give them parallelly to that the CPU or to the execution unit to execute the instructions. So in the pipeline, first these instructions are decoded and converted into micro instructions. So that is what actually going to be help. These are processed at the time at the rest of the pipeline. So this is what actually the fact here is that I mean we are the concept we have already discussed, that when the six instructions are going to be accepted by that the CPU, he is going to be break these instructions and make them the subgroups and give it parallelly in the pipeline, and that the executions are going to be happen at the same time. So that is actually we are talking about. This is what actually it is telling that okay, there's the pipeline technologies we are talking about. The pipeline is made up of a number of stages. So that means here again we are seeing that the stages. Yes, of course that the instruction cycle stages we have seen, that is a bit related with this, the pipeline stages that we are talking about. So it is talking about that okay, how many pipelines, how many stages are going to be there into the pipelines. So I say the older processor have only few, but newer processor having more pipelines, many pipelines, more pipelines. So at the stage, something is done with that the instruction, and each stage requires from the processor. That is what actually we are talking about. The tick, right? The clock tick. So we are talking about. We have discussed it onto that the cache memory also. That we have seen that. I mean, the slower cache. If you're having the level on cache smaller, and if you're having that the more bus wide, that means you will be able to get able to save that the number of clocks, the number of clock ticks. So that is going to be significantly reduce your delay, your latency. That the latency you're talking about, that is actually we know that if I'm giving the command to that the computer, it is going to be take some time. So that the time we are actually going to be talk about that okay, how long time it is going to be taken by the computer to work with. So if it is taking more time, the latency is going to be more. If it is taking less time, the latency is going to be smaller. So that is what actually we're looking for, that we should have to be reduce the latency when the computer is working with some commands. So here also that we are talking about that okay, at each stage, that the stages we are considering for the pipeline, at the each stage the something is going to be happening with that the instructions, that the micro ops you have made. So with that the micro ops, something is going to be happening at the each stage, the number of stages the pipeline has. So that is actually we should have to be, each stage requires one clock tick from the processor. So that is the fact that the stages are going to be executed, or the stages is going to be processed. That is going to be take at least one clock tick from the processor. So that is actually it's mentioning. So this is what we are discussing in the case study class, that the last slide. And in that slide, we are seeing that okay, the execution phase of an instruction for a processor with a 5-step classical pipeline are as follows. So this is known as the classical pipeline, 5 steps. Okay, so that the 5 steps you are seeing here, that what the 5 steps are there. Look at It's similar that what we have studied before, that the fetch, decode, execute. So we have seen them. So and then we are having the memory and the write back. So this is what I mean. The state we have said here, that we are having the only few stages, or only the one the newer processor having the many stages. So this is the classical one. Okay, so later on that the pipelines stages have been increased, so that actually you can get the better performance from the CPU. So this is the classical one. So that the basic classical one, 5 steps that actually we are seeing here. So fetch is telling that retrieves the instructions from the cache. Decode is telling that decode the instruction and looks for the operands, register or immediate values. And execute means the performs instructions. For example, if you're giving that an add instruction as an operand, then sorry, this that the add instruction. The add instruction is going to be the ops. That is the operation code, right? So that the add is going to be looked for, like that the page decode execute we have already studied, right? So here we have said it already, that decoding unit. Yeah, look that. So this is my opcode, right? This is my operation code, and this is my that opcode meanings, the instruction meanings. So this is that I'm talking about. That I mean, when that it is going to be the operation code is going to be the add, the execution stage. Yeah. So the execution stage, when the opcode is going to be add, on that time it is going to be know that actually it is the addition is going to be performed. So that is what the control unit is going to be know, that okay, with this instruction, from that the instruction, by seeing the opcode add, I understand that okay, I need to be, the ALU is going to be do some addition job. So by seeing this opcode, I mean, this control unit is going to be understand what actually he needs to do with that the instruction he has received. So if he's receiving that okay sub as an opcode, then he'll understand okay, I have to, that means CPU is going to be do some subtraction job. So if it's MUL, then okay, it is going to be that the multiplication job. If it's DIV, then it's okay, it is going to be the division job. If it is uh, LDR, that means it is the load. Okay, so this is that the I mean the opcode is going to be there as an indexed into that the decoding unit, and when the control unit is going to be receive this instruction, by seeing the opcode, it will understand exactly what is going to be happen with this instruction. So this is that the execution phase is going to be happen based on the opcode directions, and then the memory, that is access the memory and write back or retrieves data from it. So this is simply that the RAM that you're talking about, and write back information. So after doing that, the executions that is going to be recorded into that the general register, that okay, what is the result for that the executions, the operations like adding or subtractions, or maybe that multiplication, division. So what is the result that is temporarily going to be record into that the register. So this is that my 5 steps, the classical pipelines that I'm talking about, and I know now that what are the 5 steps are, and what are the works of them, what exactly that is going to be happen into this the 5 steps. Now you are getting here an example for basic 5 steps pipeline in a RISC machine. So you can see that this pipeline's name is going to be here with the short form. It means the instruction fetch. ID means that the instruction decode, and the EX means the execute, and MEM means that the memory access, and WMIM means that the register write back. So this is what the 5 steps. So this is making short form to show this example to you. This is a very simple example to understand that exactly what is happening. So we are talking about the pipeline. So we are talking about the 5 stages. So you can see that we are having that the 5 consecutive operations are going to be done into the pipeline. So how it is happening? Look that if it is I'm having that the first instruction into the first pipeline, that it is started with the if. Okay, so the first step, the instruction page. So when this is going to be happen, there is not going to be any other steps or any other instruction is going to be start from the if. So that means when the if the first stage is going to be execute into the CPU, that if you are considering T, then the next phase is going to be start from T plus 1. You understand that the next stage, the next instruction is going to be taken. So that is starting from the if, because the first step's already done that the if job, and second step that the ID is happening for the first instruction. So on that time, second instruction if is starting. So that the T plus 1 you have got. So that means this is going to be the T plus 2. Under the T plus 2, that the first two instructions, one is with the execution unit, another is then the ID, that is instruction decoding, and third one is started from if, the instruction page. So now if it is then the next step T plus 3. So this way it is progressing. So you can see here that I am having that the five instructions at a time in this example. So you will find it out. It is quite interesting that, I mean, there is not going to be any step that for the instructions are going to be same. What the same means that if I am having so that if, so that the other instructions are running, they should not be in the steps of if. If they are having that any one of them having that the if steps, then there is going to be the problem. Then, I mean, the CPU is going to be confused that which instruction it is talking about. So this is quite interesting that, I mean, the steps are going to be run onto that the CPU such a way so that not a common steps are going to be there with the instructions in the pipeline when they are executing. So this is what, I mean, you can see that it's saying the vertical axis is successive instructions. So the horizontal axis is time. So this is that the horizontal axis, x-axis you can think. And so in the green column, the earliest instruction is WB. So that means earlier, the first instruction actually in the last stage, register back, write back. And then the latest instruction is undergoing instruction phase. The last one is if, so that the instruction phase just it started. So this is what actually that, I mean, for all the cases you can see that for the second instruction it is into the memory access. Third instruction is that the executing, and fifth instruction is that the in the ID. Sorry, fourth instruction is the ID, and the fifth instruction is the if. So this is how that, I mean, the second instruction finish here, third instruction finish here, fourth and five. So if you're looking to this diagram, that is also going to be interesting. So you can see that, I mean, this is a puzzle that, I mean, if you're looking like that, so you'll see that they are actually, according to the time, their settings, you are going to see that it is matching. It's like that the puzzle, right?
Yes, sir.
Yeah, it's quite interesting. So that is what, I mean, this is what that the 5 stages pipeline works. So remember that what I am talking about. So that the steps, when the stages are going to, it is only the 5 classical stage. So there is a less opportunity that there is going to be the, there is going to be the any common stage for the instructions, because only 5 stages are there. But with that, when that, I mean, it has been applied and it has been seen that yes, it is very useful. You can actually do that many works at a time by giving that the works parallelly, giving that the work parallelly. It has been found that it is very efficient. It is very effective. So then what is happened? Then actually that the stages are actually increased. Stages are day by day that the stages are going to be increased for the pipeline. So it was thinking that okay, more stages is going to be there, the more faster that the executions are going to be there. So this the problem comes. Actually, this that the problem comes that, I mean, when the stages increase, on that time it can be very usual that, I mean, if you are having with that, say that if it is you are having the 24 stages, 24 stages if you are having into the other pipeline. So it can happen that, I mean, there can be a stage where that the 2 instructions are going to be into the same stage into that the in any column or any time, that it can happen that more than 1 stage are going to be into the same stage. Same stage means here that, I mean, I'm talking about a single duration. Okay, any place, a single duration. It can happen that the instructions are going to be in the same stage. That means if it is WB, here also maybe WB. It can happen. So because the stage number is more. So if it is happening, then that the problem comes. Then actually that CPU is going to be do not CPU is going to be confused that okay, the WB is for what? If the W is common, then WB is for which instruction? Or if the mem common, then which instruction is for memory access? So that I mean execution unit can be I mean confused with that. So on that time that actually called that the misprediction. The prediction is going to be happen that okay, the CPU is thinking that W is for the first instruction, but it can be for the third one. So that the executions is going to be in trouble. That there can be the misprediction. There can be I mean if it is happening that okay, there is common WB in a stage, then these two stages must need to be start from beginning. These two instruction execution must need to be start from beginning. So if it is happening, then you are going to be loser because I mean that the number of clocks it I already executed, so that are going to be I mean wasted. So those clocks are going to be wasted. That means you are going to be get the service late. So this is what actually make that the critical problem. So this if this happens, what is going to be taken into consideration? If this happens, how you are going to be overcome these problems? There are several algorithms are there to fix it up, but we are not studying it here. If you're interested, you can go to that the Wikipedia, or you can go to that the any searching with that the pipeline technology in the processor in the Google to see that I mean how they are actually overcoming those problems, that if they are coming as a common into a in the multiple stage, if that the things are common. Yeah, do you understand that?
Yes, sir. We got this topic in architecture even.
Okay, so if you have studied the computer architecture, so you know about this pipelines, I mean, a bit in detail, right?
Yes, sir.
Okay, that's good. So now you can see here that Pentium 4 and Athlon XP can decode about 2.5 instruction per clock tick. Okay, so these are the two processors decode about 2.5 instructions per clock, and the first Pentium 4 has several long pipelines, allowing the processor to hold up to 126 instructions in total. Okay, so that is what I mean. The development was that I mean when that the pipelines, several long pipelines are there. I mean you can see that so many instructions can be taken into account. But here you can see that per clock tick, the 2.5 instructions are going to be taken in that case. These all being processed at the same time, but at the different stages of execution. So that is actually we are explaining here. Okay, so you can see that I mean it is giving a table that actually you will be able to see that use of more and longer pipelines. What I mean, processor can execute more instruction at the same time. So that there is an I mean a table, a statistics has been given to understand that okay, in the case X2, that is instruction executed at the same time only 24. But day by day, that with the improvement of the processor, you can see that at the same time the instruction execution has been increased. So that it is was we are talking about here that 126 instruction in total can be executed if the pipeline is longer. So this is actually a significant improvement has been done with the pipeline technology. We can simply find it out that how much faster that the executions are going to be for the instructions. I mean, if we are having the pipeline technology. So what is actually happens in the pipeline technology? There is an actually simple example bring with this question that what is actually happening in the pipeline. So this is here you are having the two types of unit. You already know about the arithmetic logic unit, but here we are talking about the another unit. So do not think that if it is asking to you that okay, how many units or what are the units are there the CPU, do not think that ALU and that the and CU are the only unit into that the microprocessor. There are actually several units are there in the different processor. The different type of units can be there, but we say that main components. That's why we say it. What are the main components of the CPU? So if you're talking about the main components, that is the name comes with that the CU and ALU. Okay. Otherwise, that the CPU can have that the different type of units. That is actually mandatory that it need to be there into that the CPU. So here we are talking about that another unit, that the floating point unit. So this is why why we need this with that the ALU, that actually you are going to be get the information here. So you say the ALU is the calculating device that does operation on whole numbers if the number is integer. That is actually the fact here, that the operations is going to be done you understand that ALU is going to be do that the arithmetic and logic unit. So arithmetic operations, logical operations are going to be there. But when it is integers, but when it comes to the numbers with many decimal places, that is actually the fact. I mean, if the number is actually complex number, very big number, right, with the decimal places, then the ALU chokes. So ALU on that time and does not really able to work with the bigger size of the decimal numbers. So what is going to be happen then? That is actually for that is actually you're having the FPU. Say that can take a very long time to process these operations. So this that happen. This is the case is happening. That if it is the very much bigger number with many decimal places, the ALU chocks and can take a very long time to process the operations. So this is a problematic part of the ALU. That I mean, if you are taking long time for calculating some mathematical thing, then it's not going to be a good idea. So that is what the FPU is used to relieve the load. So that is what it is telling, that an FPU is a number of cruncher, especially designed for that the floating point operations. So if there is the floating point operations are there, then I mean it is going to be taken by the FPU. How it is going to be done, that we are going to see in the next slide. So typically the several ALUs and CPUs are there in the same processor. So that is what that several ALU and several FPUs. Do not think that only the it is going to be there, that only one execution it is going to be there. It can be the several ALU as well. So the different, as I said, the different processor are going to be the different design, and different processor are actually designed for the different systems, right? Like that, I mean, we know that, I mean, there is a desktop computer, laptop computer, there is the mainframe computer, mini computer, supercomputer. So it's, do not think that all that the type of that the system, all of type of that the system are in the same type of systems, the processors are going to be same. They are going to be a lot of difference between that the processor to the processor. So hopefully that from that seminar at the end of this course, that the processor group is going to be bringing a discussion about that. Actually, what are the differences among those that the processors they are going to be take from that decade by decade. So this is what actually going to be quite interesting. And you can see also that here that CPU also has other operation unit. So that is the another one talking about, that is the LSU. So what that the LSU unit is for, that load or stored, this is known as the load and store unit, load and or store unit. So through that actually the CPU is going to be maybe store something or load something, that actually you have already seen. That is actually we have already seen that the page it could execute detailed example. We have seen that how it is loading, the load unit and the store unit is going to be there. So what is actually happens in the pipelines is continuing the question. So this is that the units we are talking about. Now we are going to be get the discussions here. That what is happening. So you say processor core is right beside that the L1 cache. Okay, the processor core is going to be right beside the L1 cache. We have already seen when we have discussed about the caching, that the processor core, that L1 cache. So this is your L1 cache, and this is your L2 cache, and this is your processor core. So exactly that we can see that the processor core is going to be right just beside that the L1 cache. So that is what actually it is showing to you here as well, that this is your processor core, and this is beside the L1 cache. So that is what it is talking about. Later an instruction has to be processed. So when the instruction has to be processed, then what is going to be happen? The processor core fetches a long and complex 8086 instruction from L1 instruction cache. So that is what actually it is showing to you, that okay, from the L1 cache you are going to be take a long instruction fetch 8086. That is the decoder actually. So what it is doing? The instruction is sent into the pipeline where it is broken down into smaller units. The instruction is sent into the pipeline where it is broken down into smaller units. So that the instruction set you are having, large instruction set you are having, that you are going to be break down, that you are going to make that the micro ops, that there are going to be subgroups. So the instructions. So what is going to be happen like that? When that you are doing it, if it is an integer operation, it is sent to an ALU. So that is what that you are having the 3 units into that the processor core. So you are going to be, if it is that the integer, you are going to be send it to ALU. That though arithmetic operations, while the floating point operations are sent to the FPU. So if it is the floating point operations, then it is going to be sent to FPU that you do this operation. So after processing the data is sent back to the L1 cache. So when it is going to be when the execution is going to be done, we know already that we are going to be send it back to the memory. So that is what actually it is talking about. This description applies to the working cycle. It is for that the Pentium 3 and Athlon. So this is that the architecture you are showing. This is that the picture you are showing. That is actually for the Pentium 3 and Athlon processor applicable. Later on, that the things are actually changed and improved, or maybe that the design has been changed. So we are seeing here another example that you can see here. That here we are talking about a processor that is for the Pentium 3 and Athlon, and here we are talking about the processor Pentium 4. So look that there is already a change here. You'll be able to see it. Just a moment, I got a call. Hello.
शायद प्यार है क्या नशा
Okay, sorry. So in the Pentium 4, that the instruction cache has been placed between the instruction fetch, translate unit, and ALU, FPU, and LSU. So here the instruction cache does not store the actual instructions, but rather than the half digest micro ops. So what is happening here? What is the difference between this one and this one? So you will be able to see that what is the difference. That from the after the L1 instruction cache, the next step we have seen that instruction fetch, translate, 8086 decode. So that is actually bring on the top of the L1 cache. So first it is talking about the instruction instruction fetches, translate, 8086 decoder, that unit. To that has been being outside, and from that means this is going to be now the subgroups, that when the 8086 instructions are going to be received, on that time this is already going to be chopped down. That is going to be already the instructions are going to be chopped down, make it that the micro ops. So that after doing that, it is going to be sent to the instruction cache, L1 instruction cache. So when it will come to the L1 instruction cache, from this place itself, you're going to be know that okay, which operation is going to be needed. So if it is needed that the integer operation, if it is needed that the floating point operations, it is needed that when that you are loading something, okay, that LSU or store something, on that time this image is going to be sent here. So this is that the differences between here and here. Do you understand that? What is the difference between these
Yes,
two
sir.
figures? It's clear, right?
Yes, sir.
Okay, so that is what that the pipeline technology can actually somewhat. Definitely that. It is a technology, or that the pipeline architecture. Definitely that it is uh, going to be help processor to fetch the instructions, or to do that the operations parallelly. It is a very good technique. You can say that excellent technique that can be help CPU to do that the operations parallelly. So the length of the pipeline. So this is what actually another discussion point here. That okay, we have said that older processor is having that fewer number of stages. The newer processor are having that many more stages. So now what is going to be the length? So it says the longer the pipeline, the higher the processor clock frequency can be. Longer the pipeline, the higher the processor clock frequency can be. So is it, give us the license that we are going to be prepare that more number of pipeline stages? Does it give us license that we can prepare a 1 million pipeline stages? That is going to be a question. It is telling about the longer the pipeline, but it did not tell you that how much longer. The higher the processor clock frequency can be. So this is because in the longer pipelines, the instructions are cut into more sub instructions or sub ops, which can be executed more quickly. Definitely that you'll see here from that the list that we are having the different processors, and with that the processors will be see that day by day number of stages are increased. So this is the classical 5 stage we have seen already in our lecture, and you can see that later on it has been increased. It has been increased up to that the Pentium 4 we are seeing, but if you're going later on, then you'll see that more stages are there. So you can see that here we are having the 31 stages. So if you're looking to that the clock frequency, then you'll find it out that it is significantly improved from that the top to bottom. If you're coming, then you'll see that it is significantly improving the clock frequencies. So this is what that I mean. It has been found, it has been told, or it has been declared that okay, the pipeline technology is going to be useful, is going to be very much effective for that working with the micro ops or sub instructions to execute parallelly into that the execution unit. So this is what actually it is. It is a proof. It is a proof with the statistics that exactly that I mean number of if the number of pipeline stages are more, then it is going to be give you the more clock frequencies. So this is what that my discussion was. Yesterday also we have discussed one thing that there are different level of caches we are having that L1, L2, L3. So is it simply increasing the level of cache? Is it simply improve the performance of the CPU? So what is the answer? Yesterday we have discussed. Can anybody tell me that simply if I'm making that the cache level L1, L2, L3, L4, L5, L6, L7, is it going to be effective? Anybody? Are you listening?
Yes, sir.
Yes, sir.
Yes, sir.
Could you repeat it, sir, again?
I say that we have discussed yesterday that we are having the level 1 cache, level 2 cache, level 3 cache. So if we are increasing the levels, level 4, level 5, level 6, level 7 cache memory, then is it going to be, improve our CPU's performance or not? That my
Yes,
question
sir.
is.
No,
It is,
sir.
it is going to be improved or not? Yes or
sir.
no? No. Why? Why it is not? Yesterday only I have discussed it.
Sir, it is dependent on the number of memory we have. Like if I have less memory, having a lot of caches is not going to help.
No. That you are giving me the different information. You are telling me that why the L1 cache is going to be the smaller size, why the L2 cache is going to be the bigger size. But yesterday I have said it to you that why simply increasing the cache of level, the CPU's performance is not going to be good. So look at let me discuss it again. Listen carefully. I mean, this you should have to understand that you are having the L1 cache, you are having the L2 cache, you are having that the L3 cache, right? So why you are placing the cache? This is if you this is if it is if your CPU and if it is your RAM, then why actually you are having that the level of caches? So we say that we do not want to go directly to the RAM, right? Because if you are going to that directly to the RAM while the CPU is doing some operation, then it is going to be take some time to get back that the instructions to continue the running of that the CPU's operation. So that's why we are bringing the level of cache. So if the CPU is doing operation, it needs something, it is going to be asked to the L1. Do you have this? If it is has, then it is going to be immediately give. Then if it is not there, then cache means then it is going to be sent to the L2 request. It is there, yes. Then it is going to be give to L1 and then it is going to be done to the CPU. So if it is not there, then you are going to be go to the L3. So if it is there, then it is going to be sent to L2 and then from L2 to L3 and L1 and then the CPU. So if you're simply increasing the level of caches, so what is happening? That for an instruction, you are going to the L1. You do not have cache miss. That the instruction is not have. So you're going to the L2. It is also not there. You're going to that L3. It is also not there. Then you're going for the L4. So what exactly you're trying to do? You are wasting the time. Think that if it is, if simply you are giving that the number of level of caches you're increasing, then what is happening? That simply you are taking the time. It's not actually, it's not like that you are going to be switched from one cache memory to the another cache memory. very quickly that the way you are thinking. It is going to be time consuming and delay is going to be there. Latency is going to be there. So that's why I mean maybe that if that it is not there L3 and you're going to be the L4, and if it is not L4 then you're going to be the L5. So you're just increasing the searching. Okay, so it is then if it is like that, I mean you are having the level of 5 caches and not none of them are having, maybe the L5 cache is having the instructions. So by that time you are going to be bring that the instructions from the L5 cache memory. It is much more better to go directly to the RAM. Do you understand that or not? This is quite interesting. You should have to understand it. Do you understand it or not?
Yes, sir, got it.
Yes, sir.
Right, right. So I mean that is why simply increasing the level of cache memory is not simply going to be useful, because you should have to be think overall performance. You should have to think that okay, how much time I'm going to be it is going to be taken for actually access a thing from that level of caches. So if it is coming that we are having the 10 level of caches, it can happen that for going from the processor to the L10 level of caches, then it is maybe less time it is going to be take if you are bringing the instructions from the RAM. So why I am actually going to be have this level of caches? Do you understand it or not? So I need that much. Actually, what is going to be help me? It's not like that. Okay, I'm having the 2% in my hand. I'm doing your work. I need the 2% in my hand to complete the work. If I am bringing the 10%, then there is going to be more chaos. Okay, there is going to be the more problem to complete the work. Get it or not?
Yes, sir, definitely.
Yes, sir.
Right. I'm sorry. So look here, that problems of having more pipelines. So this is also that the same thing, same concept comes that okay, we say that the newer processor are going to be have many more stages in the pipeline. So is it actually going to be an effective one? So how many pipelines are going to be there? How you are going to be handle them? So if there is, I mean, more pipelines are going to be there, then what is going to be happen? So that is actually the discussion point. So we say more and more parallel pipelines in one CPU is not the solution to improve the performance of highest level. So this is again, I mean, this is again that interesting for the pipeline that we have seen for the caching memory. Now we are talking for the pipeline. Yes, it is not. It is not a solution for improving the performance to highest level if you are having simply more and more pipelines. So yes, of course, the pipeline technology is an efficient technology, a good technology to deal with that the instruction set that you're getting. But it's not simply that. I mean, if you're increasing that the number of stages, if you're having more and more parallel pipelines, it is simply going to be help you to improve the performance of your CPU. No, do not think like that. That is they are telling. So what is that the problem? Why we are telling it? So you can see some of the information here. Say the processor core is simply not utilized efficiently enough because data cannot be brought to it quickly enough. So this is one of the problem that I mean you're having the more and more pipelines. It is not going to be simply helpful, and simply your performance is not going to be high level. Why? Because the processor core is simply not utilized efficiently enough because the data cannot be brought to it quickly enough. Okay, so another problem is having the several pipelines arises when the processor can decode several instructions in parallel. Okay, so having several pipeline arises when the processor can decode several instructions in parallel, each in its own pipeline. So this is that already I have said. For this reason, I have already said this, that the miss prediction can be there, result in a number of wasted clock ticks. Can you remember? I was discussing here. That I mean, it can happen that if you're having only the simplified stage, and we can see that there is no duplicate. No duplicate stage, no common stage while that 5 instructions are running at the same time. But if you're having that the more pipelines, that means you're going to be dealing with the more instructions, 1 to n instructions you're going to be dealing with. So when it is going to be happen, you are taking the more pipelines. On that time, it can easily happen that that some of the stages are going to be duplicate. So at the same time, if that the duplicate stage is going to be there, then it is going to be a problem for CPU to understand. It is going to be a misprediction can be there. So which instruction maybe that for the instruction number 1 you are dealing with, that is in a stage, and instruction number 11 you are dealing with, that is another stage. So if that, I mean, at the same time, if they are in the same stage, then I mean, CPU can misunderstand that which stage instruction it is. Is it that the 1 number, or is that the 11 number? So that is what the misprediction can be here. So on that time, simply if that this misprediction is happening, then you should have to start the instruction execution again. So this is the quite interesting thing. So I'm thinking that, okay, if I'm going by that, I mean, if I want to climb a roof of the building, so if I'm thinking that, okay, I can go by stairs, I can go by the lift, and I can go by that a pipe that is outside of the building. I mean, with it is actually, the pipe is actually going from the ground to the roof,
Yes, sir.
right? So I
Climbing
mean,
up.
the problem can be there. Right. So it can happen that, okay, that you are trying to climbing through the pipe. So it can happen that, okay, you can be confused. Okay, so in the midpoint maybe you can fall down and you can die. Okay, so you should have to think. I mean, the different ways are there. The different pipelines are there. That it's not simply that many pipelines are going to give you the better solution. You should have maybe that the pipelines are there for climbing from the ground to the roof. If there are few pipelines, okay, you can actually think that, okay, I can climb this. But if there are many pipelines are there, maybe you can going to be confused that which one is going to be better one to climb. So it can happen that, I mean, it is actually happens in Bangladesh. I can also remember when I was in college. So that time the Nagarbaul James came to that Noshindi College. Okay, so I have seen that, I mean, many students of that our college was trying to trying to go to the roof of the building so that they can enjoy the concert from the top of the roof. So that on that time all the gate was locked, that you cannot simply climb the stairs because all the buildings doors and gates are locked. So people are just simply climbing on the top of the roof by using those pipelines. So it was quite interesting. Actually, I just remember when I was discussing this. So anyway, so this misprediction is going to be happen. So if that the misprediction is going to be happen, so that is a different example. Do not actually confused with this the pipeline we are discussing here and that the outer side, the example I have given. So this is actually completely different. That, I mean, if you are having the more pipelines, what is going to be the problem is that at the same time that the stages for that the two instruction, it can be same. So you can see that there is no common that is WB, name, X, ID, and if. So that the 5 instructions are running at this moment parallelly into a processor. So none of them are in the same stage. None of them are in the same stage. So that is why there is no problem that 5 instructions are going to be safely executed into the processors. But if you are not having, if you are having a common stage into that at the same time, that the problem comes. That the processor confused. It can, don't think that it can be only 2. It can be more. It can be 3 instructions at the same stage at the same time are they are having in the same stage. It can be more. It can be 5. It can be 10. Depends on that. I mean, the stages you are having. If you are having the 100 of stages into that the pipelines, so that means in the 100 of stages, it can be happen that 20, 30 stages, 30 instructions at a time in the same stage. So definitely the CPU is going to be confused that which one I should take, which one is for the instruction is for what, which execution I'm going to be take. Do you understand that? There is going to be misprediction. There is going to be misunderstanding by the execution unit that how I am going to be executed. So what is going to be happen? So you should have to be start those execution from the beginning. So that is actually creating the problem. That, I mean, you may finish that if your 100 stages are there, if you may finish that the 90 stages out of 100. So what is going to be happen on that time? You should have to be start from beginning. So why you are then using the pipeline technology? It is much better that actually with our pipeline technology you could move down. So that is what the problem comes. That is what the misprediction can come. So this is what they did not actually stop by thinking that, okay, if I'm increasing the number of pipelines, I'm increasing the number of stages, then if there is misprediction can be there, but for that also I have some solution. Okay, so that is not the fact that I don't want to start it from the beginning. I have done already that my 10 steps, so I could not return it from that the first step. So this is what the branch prediction unit is there. So if there is something, some problems are there with that the prediction that okay which instruction is for which stages, then it is going to be decided with that the branch prediction unit. So that is going to be make you accurately find out that okay which instruction is happening for which micro ops or which stages. You understand that? So which constantly attempts to gauge the correct instruction sequence so that you do not misunderstand that okay which instruction is for what you need. Do you understand that?
Yes, sir. Got it.
So this is also a quite interesting discussions actually if you are try to read and try to understand that what is happening inside the pipelines. So anyway, so this is what that we are finishing the discussions of our processor topic. So our class time is over. So I think that in the next class, in the next week, you are going to be get the questions for that lecture number 3. So do you have any questions or any comments, anything into your mind?
No, sir.
Okay then. So thank you very much, and let's meet into the next week. Take care, all of you.
Thank you, sir.
Okay, sir. Assalamu alaikum.
Okay, so.
Thank you, sir.